A metric space is a pair x, d where x is a non-empty set and d is a function called a metric or a distance function, defined on the Cartesian product x cross x into the real numbers r. For this to be a metric, it must satisfy some axioms. That is, a metric space x, d will be a metric space if it satisfies given axioms. And the first of these axioms is the non-negativity d of x, y is greater than or equals to 0. And this tells us that the given value for our distance must never be negative. The second one is if and only if x is equals to y for where our d of x, y is equals to 0. And the third one says d of x, y must be equals to d of y, x. And the fourth one, we have d of x, y must be less than or equals to d of x, z plus d of z, y. And this is involved in the triangular inequality. Now let's go to the types of metrics. We have the usual metrics, and this usual metric usually works on more than one point. And when we talk about point, we talk about distance. And the second one is the discrete metrics, and this works on at least 2 points. It works on only 2 points. It is limited to only 2 points. So we can be having the distance between 2 points, and we are checking to see whether it's a metric space. Now let's get the overall idea about the metric space. Now we look at the diagram above, we can see that this diagram above clearly illustrates what a metric space is. Now, and we can actually deduce from this diagram above the interpretations of each of the following axioms. Now, when we look at the first axiom, we'll see that we have our distance between any of these 2 points to be greater than 0. We can see there's a distance between x and y, and there's also a distance between x and z, and there's a distance between y and z. And we can see from the given distances, we can see that our value can never take any negative number. For the second property, we can also see right in there that the only way we can have our distance to be 0 is only if x and y are on the same point. So the only instance where we can have a 0 is when x is equals to y. And then we can also examine from the above diagram for the situation where we have d of x, y is equals to d of y, x. No matter how you switch the position where we are going to take our distance, you always notice that the distance between the two given points x and y will always be the same, irrespective of your starting point or your ending point. If we start from x, we take our distance from x to y, we measure, and we start from y, we take the distance between y and x. You still see that it is the same. So the symmetric property holds. And also the fourth property, which is the distance, the triangular inequality, we can see that we have a distance between x to y, and we also have a distance between x to z, and we also have a distance between y to z. And we can see from the diagram that the distance between x to y and y to z may not necessarily be equals to the distance between x, z. And from the given diagram, we can deduce that the arc length between x along the path onto z is actually greater than the distance, the straight distance, the displacement between x to z. So in this diagram, we can see that the distance, adding the distance between x to y and y to z is obviously greater than the distance between x straight up to z. In the next episode, we will be talking and diving into the types of matrix, and we will be giving some examples. Goodbye.